Now, the third topic, that is on binary coded genetic algorithm. So, here actually what we do is the design variables, those are expressed in terms of the binary codes. Like if I have got a function like y is a function of say 3 variable like x 1, x 2 and x 3, and let me take that out of these 3 variable, say x 1 is a real variable, x 2 is an integer variable and x 3 is once again a real variable. So, each of these particular variables are having their own ranges. Now, within this particular range, so what we do is we will have to explain, we will have to represent. So, this particular variable, and to represent each of the variable we use some binary codes. For example, say depending on the accuracy limit or the precision we need. So, we will have to assign some number of bits to express this particular x 1. Supposing that say I am representing, I am using say 10 bits to represent x 1, then I am using say 6 bits to represent say x 2, and I am using so once again the 10 bits to represent say x 3. So, the GA string will be 10 plus 6 plus 10. So, it is nothing but 26 bits long. So, I will have to use the 26 bits long GA string, and here in binary coded GA actually as I told, the variables are coded in the form of the binary number. Now, once you have coded this particular in the form of binary, so let us see how does it work. Now, the working cycle of a GA. Now, here actually what we do is we start with a population of solution. Now, if it is binary coded GA, we start with a large number of binary codes, binary strings. For example, say if the population size is 100, so we use 100 GA string, and these particular GA string, those are generated at random using the random number generator. Now, once you have got the number of bits to be assigned to each of the variable, now I can find out the decoded value for each of these particular the substring used to represent the design variable. And once you have got the decoded value and knowing their respective ranges and using the linear mapping rule, so we can find out what should be the real values for these particular the real variables, and those decoded value will be the values for this particular the integer variables. And once you have got the numerical values for this particular so this the numerical values for the design variables. So, I can find out what should be the value for this particular the objective function, that is y, and for the whole population of this particular binary coded GA. So, if this is the initial population of the binary coded GA, so I can find out for the whole population of size n. So, I can find out the fitness information. So, these are nothing but the fitness information for the whole population, and once you have got the fitness information for the whole population, now we are in a position to decide out of these n solutions which are good and which are bad. Now, to decide which are good, which are bad, we take the help of one operator, that is called the reproduction operator. Now, the purpose of using this reproduction operator is to form a mating pool. Now, as this initial population is generated at random, so there is no guarantee that all the solutions will be equally good. There could be a few good solutions, there could be a few bad solutions also. Now, if you find out some good solution, so in the mating pool actually we are going to take multiple copies of this particular good solution, and if you find some bad solution in the initial population, those solutions we are going to delete from this particular the mating pool. The philosophy behind going for this mating pool, that this particular mating pool will consist of good solution probabilistically. Now, if it is a maximization problem, so if I take the average fitness of this particular mating pool, the average fitness of the mating pool is expected to be more compared to that of this particular the initial population. Now, if you see the literature, we have got a few reproduction scheme. For example, the oldest one is nothing but the proportionate selection or the roulette wheel selection, where the probability of selecting a particular solution is proportional to the fitness. So, the higher the fitness, the more will be the probability of being selected in this particular the mating pool. That means, if we find out some solution whose fitness is not good, there is a possibility it will be deleted from this particular the mating pool. Now, this particular the proportionate selection, that is the oldest method of reproduction, has got one drawback, that there is a chance of premature convergence, and to remove that particular problem. So, another reproduction scheme was proposed, and that is nothing but the ranking solution. Now, in ranking solution, actually what we do is, in ranking selection what we do is, we do the proportionate selection based on the ranks, but not based on the fitness information. So, based on the rank we do this particular proportionate selection, and by doing that we can remove the chance of this premature convergence. But nowadays actually we use some sort of tournament selection, and in tournament selection we select a tournament size, and those solutions are selected at random from this particular initial population, and we try to find out the best, and the best one is selected in the mating pool. And once we have selected the best one in the mating pool, so all the solutions considered in the tournament will be returned back to the initial population, and if the population size is capital N, so we will have to play the tournament for capital N size n times, and each time we are going to select a particular the solution. Now, if you see the computational complexity, the computational complexity of this particular the tournament selection is much less compared to the proportionate selection, and that is why nowadays we use only the tournament selection. Now, once we have got this particular mating pool, next we try to form the mating pair, and this particular mating pair selection is done at random. Now, supposing that we have got n population size, so there will be n by 2 mating pairs, and in each pair there will be 2 such solution, and this particular mating pair selection will be at random. Now, supposing that we have got n by 2 mating pairs. Now, for each of the mating pair, whether it is going to participate in the next operation, that is the crossover. So, we try to take the help of one probability, that is called the probability of crossover. Now, depending on the probability of crossover, we take the decision whether this particular mating pair is going to participate in crossover or not. Now, if it participates in crossover, there will be exchange of properties, and due to this particular crossover operation, so starting from the 2 parents, in fact, we are going to get like 2 children. Now, if you see this particular the literature, we have got the different types of crossover operators, like for example, say we have got the single point crossover. So, we have got the single point crossover, then comes we have got the 2 point crossover, then comes we have got the multi point crossover, and we have got the uniform crossover. So, these particular crossover operators we generally use just to find out the children solutions from the parents, and there will be exchange of properties due to this particular crossover, and there is a possibility some new properties are going to come in the children solution. Now, once we have got this particular children solution, next we go for the mutation operator. Now, in mutation operator there will be actually sudden change of parameter, and this particular mutation operator is going to help us to come out of the local minima, if any. And using this particular this mutation operator, generally we go for the bitwise mutation, and using this particular bitwise mutation, so there is a possibility that we will be able to come out from this particular local minima problem, and the GA is going to hit the globally optimal solution. So, this completes actually one iteration of the GA, and this particular process will continue for a large number of generation or the large number of iteration. Then GA through a large number of iteration we will try to find out what should be the globally optimal solution. So, this is the way actually one binary coded GA works. Now, if you see the merits and demerits. So, this particular binary coded GA has got a few merits and demerits that I am going to discuss after some time, but before that let me tell you that we actually carried out some hand calculation just to show you the working principle of a binary coded GA, and by doing that particular hand calculation, in fact, we could prove indirectly that GA can optimize the function and GA can find out the optimal solution through a large number of iteration. Now, if you want to ensure a very efficient search for the GA, so we will have to select the parameters in an optimal sense, and that is why we will have to go for this particular the GA parametrics GA parameter setting. Now, the performance of a GA depends on a balance between the population diversity and the selection pressure. So, there are two things, one is called the selection pressure and another is called the population diversity. Now, this population diversity and selection pressure, there should be a proper balance if you want to ensure a very efficient search for this particular the GA. Now, let me see what happens if the selection pressure is too high. If the selection pressure is too high, there could be a chance of premature conversion, and if the population diversity is too large. So, there is a possibility that there will be enough search, but it may take long time to reach that particular optimal solution. So, there should be a proper balance between selection pressure and this particular the population diversity in GA, and to ensure that we generally go for some sort of parameter setting, like we try to set what should be the optimal parameters like probability of crossover, then probability of mutation, then population size and the maximum number of generation. Now, we use a particular method of GA parameter setting. Here one parameter is varied at a time, keeping the other parameter constant, and this is an approximate way of doing. So, using this approximate method of GA parameter setting, we can find out what should be the near optimal GA parameter. Now, if you run this particular GA using that particular near optimal parameters, there is a possibility that it will be able to maintain the balance between the selection pressure and the population diversity, and GA will be able to hit that globally optimal solution. So, this is actually the purpose of the GA parametric study, which I have already discussed in much more details. Now, the next topic is the schema theorem of this particular the binary coded GA. Now, actually the purpose of this particular schema theorem was to prove indirectly the convergence of this particular the binary coded GA. Now, here as there is no such direct mathematical proof till today of this particular the GA. So, we took the help of this schema theorem just to indirectly prove that yes, GA can maximize or minimize, GA can optimize that particular the objective function. Now, here actually what we do is, now let me just tell you in short, in details I have already discussed. Supposing that we have got one population of solution of binary coded GA of size say n, and we have got a few binary strings here, say large number of binary strings here, and we try to find out the similarity among this particular the binary string, and after watching this particular similarity. So, we try to design one schema, and this schema is nothing but a template. So, we try to find out a template which is followed by the large number of your the GA string. the binary coded GA string. And this particular schema or the template, we try to see the growth or the decay through a large number of iteration. And mathematically we can actually derive one expression, and that expression is known as the schema growth expression, the schema growth theorem. So, this schema growth theorem we can find out one mathematical expression, and once we have got that particular mathematical expression, now we can take the decision whether a particular schema is going to survive or not, and whether this particular schema or the template is going to get a large number of your solutions or not. Now, this actually mathematically we can find out one expression, and from this particular expression we can come to one conclusion that if I have got a schema which is having short defining length, short defining length, then low order, and if the average fitness of this particular schema is found to be more than the average fitness for this particular the whole population, and that is called the schema fitness. So, if the schema fitness is found to be more than the average fitness of this particular the whole population, so there is a possibility that I will be able to find out. So, this particular schema will receive the more and more number of copies in the as the iteration proceed. So, if I have got a schema which is having short defining length, low order, and fitness is higher than the average fitness of the population, that particular schema is known as the building block. So, this is nothing but the building block for this particular your GA search, and this building block is going to gain a more and more number. If it is a good building block, it is going to gain in number through a large number of iteration, and that is going to win at the end, and this particular building block is going to indicate what should be the globally optimal solution. So, using this schema theorem or the building block hypothesis, so we can say that if there is a good schema, so that particular good schema is going to gain in number through a large number of iteration, and that is going to dictate the whole population, and that is going to indicate or going to give the globally optimal solution. Now, this particular schema theorem is actually an indirect proof for the convergence of this particular the binary coded GA. Now, here this binary coded GA has got the schema theorem. This is a plus point because many people did not initially believe the binary coded GA, but after this schema theorem was proposed, people started believing. So, this particular the binary coded GA. Now, here this building block hypothesis I discuss in details. I also solved one numerical example like how to find out the defining length, how to find out the order of a particular schema, how to find out the schema fitness, and how to find out whether a particular schema will receive more number of copy or it is going to decay. So, that type of decision we can take. So, just to explain that I took the help of one numerical example in this particular the course. Now, I am just going to concentrate a little bit on the limitation of this particular the binary coded GA. Now, we have already discussed that the accuracy depends on the number of bits assigned to represent a particular the variable. Now, if you need more accuracy, so we will have to assign a large number of bits, and supposing that I have got a function which is to be optimized. So, y is a function of say 10 variables x 1, x 2 up to say x 10. So, I have got 10 variables and I want a very good precision in each of these particular say 10 variables. That means, we will have to assign a large number of bits, might be say 20, 30 or 40 bits. Now, if I assign say 20 bits to represent each of the variable, So, there are 10 such variables. So, 10 multiplied by 20. So, your GA string will be 200 bits long. Now, if the GA string is longer and for its effective processing, so I will have to use a large population size. So, might be if it is 200, I will have to take n equals to say 1000. So, there will be huge computation and GA will become very complex, computationally very expensive, and it will become slower and slower. And that is why, because this type of algorithm, the binary coded GA, the computational complexity is actually L log L. So, L multiplied by log L is the computational complexity, where this capital L is nothing but the total string length, and if L is large, so the computational complexity is going to increase. And just to overcome, so this type of problem, so actually we try to take the help of the real coded GA. So, the binary coded GA is not going to help us to achieve your arbitrary precision which we need in the values of the variable. So, this is one of the drawbacks of this particular the binary coded GA, and another very important drawback is nothing but the Hamming cliff problem. Now, this Hamming cliff problem is actually a very difficult problem faced by this binary coded GA, because in binary codes from one number, if I want to move to the next number like or the previous number, the number of change which I will have to consider in the values of the bits is not kept the same. For example, say let me take a very simple example, say 15 to 16 if I want to go and 15 to 14 if we want to go, the number of change to be incorporated in the binary representation is not exactly the same. So, I will have to go for the different number of changes if I want to move from a particular number to the previous number or to the next number. So, actually, so this particular the problem is known as the Hamming cliff problem of the binary codes. Now, this Hamming cliff problem is going to create some sort of artificial hindrance to the gradual search of this particular the genetic algorithm. Now, if the GA search is proper, so this particular search has to be gradual and there should not be any abrupt search, and that is why. So, this particular Hamming cliff problem of the binary coded GA is not desirable, and to solve this particular Hamming cliff problem actually we take the help of another type of GA, that is called the gray coded GA. So, we take the help of this gray coded GA. Now, this particular gray coded GA is going to help us just to remove this particular the Hamming cliff problem of the binary coded GA. Now, here actually this real coded GA I have discussed in much more detail, but the gray coded GA most probably I did not discuss in detail, but it is very simple. Only thing the design variable should be expressed in terms of gray codes in place of the binary code, other things will remain the same. Now, the next is actually we discussed little bit on the constraint handling in genetic algorithm. Now, genetic algorithm can solve actually both the unconstrained as well as the constraint optimization problem. Now, here if you want to solve the constraint optimization problem, so we will have to take care of these particular the functional constraint. Now, these functional constraint actually it could be nonlinear function of the design variable, it could be the linear function of the design variable, and it could be either equality or it could be inequality functional constraint. So, all the functional constraints actually you will have to consider, and GA will have to find out one optimal solution which is feasible in the sense that it is not going to violate any of this particular the functional constraint. Now, to ensure that actually what we do is we take the help of one approach, and that is called the penalty function approach. Now, this penalty function approach in fact I have discussed in much more detail and I have solved one numerical example. Now, in short let me tell you that like how to implement this particular the penalty function approach. Now, supposing that say I have got a function, say y is a function of say 2 variable. For simplicity, let me consider that this is a function of only 2 variables. Now, using these 2 variables I have got some say objective function, say this is the objective function and I have got a few functional constraint. For example, say let me take a very hypothetical functional constraint like x 1 square plus x 1 x 2 minus x 2 square should be greater than equals to 5.0. So, this is a functional constraint, nonlinear functional constraint, inequality functional constraint. Now, if I want to solve with the help of a genetic algorithm, so genetic algorithm will have to find out those values of x 1 and x 2, so that it satisfied this particular the functional constraint, and if it does not satisfy, so this particular functional constraint, so that will be declared as the invalid solution and that is not be will not be considered as the valid optimal solution. Now, how to ensure and how to penalize if there is any such violation of this particular the functional constraint. Now, supposing that I am solving say one say minimization problem, say and I have already got the objective function, the value of the objective function is a small f and I am just going to solve one minimization problem. That means, lower the value of the objective function, so better will be the solution. Now, here if there is any such violation of the functional constraint, so I calculate the modified fitness capital F and that is nothing but small f plus a penalty term p if it is a minimization problem, and if it is a maximization problem. So, this particular the penalty term has to be. So, this is for minimization problem, this is for minimization problem and f is nothing but small f minus p, it is for the maximization problem. Now, how to calculate this particular penalty? So, this penalty is calculated using the different approaches. Now, one is called the static penalty, another is called the dynamic penalty and we have got the concept of adaptive penalty. Now, in static penalty actually what we do is we use some constant penalty value, generally we consider some high value and this particular high value is calculated with the help of some user defined the constant terms. The in details those mathematical expression I have already discussed. So, I am not going for that, and this dynamic penalty and this adaptive penalty are going to vary. It is going to vary for example, if you see this dynamic penalty, so it is going to vary from iteration to iteration, and to calculate the penalty term in the dynamic penalty approach. So, we will have to include the iteration number also. So, this particular penalty term is going to be updated with the number of iterations. Now, if I consider this adaptive penalty, so here the concept is slightly different. Now, in calculating the adaptive penalty term, so it will depend on the nature of this particular this thing nature of this functional constraint also. So, here if there is no such violation, so there will be one penalty term which is having some low value, but if there is a violation, so there will be a penalty term which is having some high value. On the other hand, if I go for the static penalty and the dynamic penalty, so if there is no violation, the penalty term will be put equal to 0. Now, using this particular penalty term, so I can find out what is this modified fitness, that is capital F. Now, you will have to go for reproduction based on this particular the modified penalty, this modified fitness, and based on the modified fitness we go for the reproduction scheme just to get this particular the mating pool, and once you have got this particular mating pool, then we go for your the crossover mutation and others, and that will complete the iterations of the GA. And by following this particular method through a large number of iteration, so we will be able to find out, the GA will be able to find out what should be the globally optimal solution. Now, this is the way actually we can use the penalty function approach to handle the functional constraint in this particular the genetic algorithm. Now, this genetic algorithm has got a few advantages and disadvantages. Now, it has got an advantages, for example, so it can tackle a variety of problem. So, it is much robust compared to the traditional tools for optimization, and so if there is any discontinuity of the objective function, so it can handle, because it does not require the gradient information of this particular your objective function. And there is another big advantage that we can go for parallel computing. As this is a population based approach, so easily we can implement that parallel computing with the help of this MPI algorithm. Now, it has got a few drawbacks. For example, the genetic algorithm is computationally very expensive, it is slow, and in fact, it is bit difficult to implement online if you want to get the optimal solution within a fraction of second. So, the conventional genetic algorithm cannot be used, and this genetic algorithm is actually a black box sort of thing. For example, say if you want to solve one maximization problem or minimization problem. Now, on the computer program of the genetic algorithm, we just write down the expression of the objective function, we give the range of the variables, and we also decide all the GA parameters, and we run GA. Then after a large number of iteration, there is a possibility the GA will be able to get that globally optimal solution, but in fact, the user may not know actually what is happening inside the GA, and that is why we call that genetic algorithm is nothing but a black box. Now, these are all disadvantages. So, there are some merits and demerits, and these are all disadvantages of this particular the genetic algorithm. Now, considering the weakness of this particular genetic algorithm, that is the genetic algorithm cannot handle the local optimization very efficiently, we take the help of one hybrid optimization tool, and that is actually efficient optimization tool. Now, sometimes we will have to use this type of efficient optimization tool, which is nothing but a hybrid optimization tool. Now, as we note, the genetic algorithm is actually a very powerful search technique for global optimization, but its local search capability is not so good, and that is why we combine the global search capability of genetic algorithm along with the local search capability of a local search technique like say steepest descent algorithm, just to efficiently solve that optimization problem. And that is why the concept of this efficient hybrid optimization tool came into the picture. Thank you.